Day 9, and here we go. This rope bridge creaks as you walk along it. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine though. The bridge spans a gorge which is carved out by a massive river far below you. You step carefully as you do. The ropes stretch and twist. You decide to distract yourself by modeling rope physics. Maybe you can even figure out where not to step. Consider a rope with a knot at each end. These knots mark the head and tail of the rope. If the head moves far enough away from the tail is pulled towards the head. Okay? Due to the nebulous reasoning involving plank links, you should be able to model the positions of the knots of a two-dimensional grid. Then, by following a hypothetical series of motions, your puzzle input, for the head, you can determine how the tail will move. Due to the aforementioned plank links, the rope must be quite short. In fact, the head and tail must always be touching, diagonally adjacent, and even overlapping. Both count as touching. Okay. So if the head is ever 2 steps directly up, down, left, or right from the tail must also move 1 step in that direction so it remains close enough. So head moves, tail follows. Okay. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. Okay. You just need to work out where the tail goes as the head follows a series of motions. Soon the head and the tail both start at the same position, overlapping. For example, R4, U4, L3. Okay, so this series of motions moves the head right 4 steps, and presumably the tail follows 4 steps, then up 4 steps, then left 3 steps, then down 1 step, and so on. After each step, you'll need to update the position of the tail if the step means that the head is no longer adjacent. After simulating the rope, you can count up all of the positions the tail visited at least once. In this diagram, S again marks the starting position, which the tail also visited. And pound marks the other positions the tail visited. So follow it along in this pattern. There are 13 positions the tail visited at least once. Simulate your complete hypothetical series of motions. How many positions does the tail of the rope visit at least once? Okay. The thing is, we don't actually even really need a grid. We just need to keep track of the head position and the tail position. And we're just gonna, for simplicity's sake, we can start them both at 0, 0. And to keep track of places it went to more than one, or at least once, what we also can do is we can just do a set, basically, of some sort of concatenation of the position, and whatever the size of that set is at the end, that's our answer. Okay, so then the next thing we need to do is basically just loop through our input. Our input is coming in as a list of strings, and then we're going to want to break them apart into 2 pieces, right and to direction and number. While we can certainly probably just update by 4 each time, or by however many it's in here, and then try to figure out the tail, it's going to be a lot easier to do the tail position specifically if we only have to worry about 1 step at a time. So probably easiest on that is we'll just make a new function for move head. And it'll take in a head, which is a position, and a tail, which is a position, and then I guess a direction. So basically, when direction up, then we're going to need to do some block here, and the way the tail follows is going to depend on the direction it moved. I mean, it doesn't have to exactly, but it will make it easier. And then for up, basically we just need to increase the Y position by 1. Head.y plus plus, great. And then we need to check if the tail is, we only care about the direction where, so the head's moving upwards, so we only care if the Y position is off more than one. We don't care about the X position because it should have already been correct. So if that's the case, then if tail.y after the move is going to be less than head.y minus 1, or yeah, so if it's more than 1 off. So we don't want to say tail by y plus plus, we actually just want to say tail.x equals head.x, and tail.y is equal to head.y minus 1. Which I think should be there. So then we basically just want to do this for all 4 cardinal directions here, and our move head function should be good. And so and we'll go ahead and put this in a int for I in 0 until distance, say positions, I guess, is equal to move head, tail. I could have made these a lot shorter names. It's okay. And then direction. Cool. And then what we next want to do is we want to add to our set. Oh, that's why it's complaining about positions. Well, we don't even need that, so it does not matter. All right, so positions dot add tail position, and then we just want to return positions dot size. Okay, and let's see if that has any chance of working. All right, so heads at 0, 0, tails at 0, 0. We're gonna remove right 4. So we go 4, tails at 3, positions is 4. Wait, why is... So first off, why is it have a size of 4 if they're all the same? And they're all the same pointer too. So obviously that's the mistake, is need to do a new position. I think that's probably the only mistake. That's the right answer. Okay, so that was the only mistake, is I accidentally object the tail position object instead of actually putting a new position each time. I don't know why it counted up from there. I guess it's because it never actually hit the same place twice, and so it never actually did a check. That's the only thing I can think of. But either way, continue to part 2. A rope snaps. Suddenly, the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping toward you as you fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how to arch your body to avoid being hit. Well, then you're dead because you can't run this computer program. So game over. All right. Good run. Fortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you must now simulate a rope consisting of 10 knots. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it using the same rules as before. Using the same series of motions as the above example, but with the knots marked H, 1, 2, 3, 4, 5, blah, blah, blah. The motion now occurs as H, H1, H1, 2, right? So obviously all of them are still here except for H and 1. So forth. And so in this case, we don't really, for each knot, we don't care about where the head moves. We only care about where the prior knot moved, because that's going to move that knot in the exact same rules that we did before. So we can use the same function that we did before. It's just going to get jumbled in there. Now you need to keep track of the positions for the new tail, number 9. Visits. In this example, the tail never moves, and so will only ever visit 1 position. However, be careful. More types of motion are possible than before. So you might want to visually compare your simulated rope to the one above. Here's a larger example, and these motions occur as follows. Okay, we'll get to this example here in a second. I think their output is exactly the same. Okay. So we want, for the first one, we just want to, we can use our same input and test data, and we just want to hit one spot. And then what we're going to do is we're going to keep an array, I guess, would be the easiest way of this. So we want just val knots equals an array of position 10 size with it is 10, right? Is H through 9? Yeah. With each starting as a position of 0 and 0. And then for each spot in the distance, we want to not move the head. We want to move each knot. Okay, so earlier on I said we could take a shortcut by only caring about the direction that the head moves and using that as a way to figure out which movement our rope needs to take. That was wrong. The problem being that the rope basically can become a chain. So if you imagine like a circle, if the head moves continually in that circle, it's dragging the next one and the next one, the next one. And so the movement from one knot to the next knot is not necessarily going to be in the same direction that the head moved. So basically I had to debug that and then rewrite some stuff for it. And I'm just going to kind of walk through the encode instead of having you watch through a bunch of boring debugging video. So first off, I split the movement stuff into two functions. I have a move head function, which basically just does what we did before. Whatever the direction is, it makes that transformation on the head. That's it. And then I have a move knot version, which does not move the head. It only moves the tail based off of the head's position relative to the tail. So if it's if the row is off by 2, then it will move the row up, and then but also check to see if it needs to move under it or diagonally to it. So like again, if you're pulling it in multiple locations, if it's going to be pulled under or if it's going to be pulled kind of in line with it. And then we'll do the same thing for all 4 of those. And then for part 2 then, basically what we're going to do is move the head, and then for every knot in there after the head, we're going to move that knot. So from the head position to the first knot to the next, or the first knot to the second knot and so forth. The move knot function also returns true if the knot moved. It returns false if the knot did not move. So if whenever we have one that doesn't move, we can just go ahead and get out of that loop. And then once we've moved the entire chain, then we can add the tail position to our set. Other than that, everything is basically the same. Okay, and 2485. Okay, let's go put that in. Yay, the right answer. You've completed day 9. All right, second half, a little frustrating. All right, well that's it for the day. All the updated code, cleaned up and everything is of course in the GitHub. And then I will see you guys tomorrow.